Okay, everybody, so I've titled this video The Derivative, Finer Points About the Concept. And I think what that means is some people will turn it off right away when they start watching the video, okay? The finer points of the concept are not for everybody. Um, different students in the class have different standards for what they want to learn and so on, and that's fine with me, and I'm not judging anybody. But if we're going to cover calculus, I should talk about some of the, I guess you could say, philosophical aspects of the derivative, conceptual aspects of it. I'm not really going to work any problems. There's nothing in the quiz that's on here. And so, like I said, many of you will turn it off right away. But for those of you that are curious to understand calculus as much as you can, then this video I think is for you. Okay, so we'll do a little thought experiment, but this is not totally a thought experiment because this is an experiment that we could actually conduct. And with the right measuring devices, we could put exact measurements on everything that's going to happen here. So let's say that we're at the top of I don't know, a cliff or something like that, maybe the top of a building or a tower, and we drop a rock from a height of 500 meters. Okay? All right. So, and it starts to fall, but from a position of 500 meters above the ground, we could measure some things about this. We could measure time with the clock, and we can measure position with a vertical axis that's imposed on the situation. Okay? Now, think about it. Before I give any math, isn't it true that the position of this rock as it falls to the ground is a function of time? And what I mean is that at any one moment of time, the rock has to be somewhere. It's got to be at some position. It can't be two places. And it's not impossible to predict where the rock is at any moment. All right? Okay, so it turns out that if we can accept that position is in fact a function of time, in this case where the rock is under the influence of gravity, that you can actually get an equation that will track its motion as it falls to the ground. So here it is. This is how position is a function of time. S is the position on this axis as it falls, 0 being where it hits the ground, 500 where it's dropped from, and T is time in seconds, okay? So you give me like T seconds, I can put it in here, and I can calculate S, where it is along here as it's falling. Okay, so that's what that does. Now, this does do some things like neglect air resistance, and if the rock is extremely dense and heavy, we don't have to consider air resistance or wind or things like that. But if you take physics 1, then you can learn from the kinematic equations how you can derive this. But let's just accept it, okay? Let's accept that I'm dropping a rock, it's falling down, we're measuring time and position, and this is the equation by the laws of nature that governs what it's going to do. Okay? All right. Now from here, I ask a few things. Okay? If I gave you that equation where position is a function of time, okay, position is in meters, time is in seconds, then could you calculate ds over dt when t is 9.5? What's that? The derivative of s, position, with respect to t, time, at the moment, at the instant when t is 9.5 seconds. Okay? Now, that on its own shouldn't be too bad at this point. You've probably practiced the rules for finding derivatives, and it probably won't be too much of a mystery for you. But if you look at this 500 minus 4.9 t squared, you find the derivative of that, ds over dt, that's negative 9.8 t. Okay? All right, and then it was to evaluate the derivative at t is 9.5. So I put 9.5 in, and I get this number, negative 93.1. Now, there's more to this number than the number itself. First of all, the negative means that it's falling. The position S is becoming smaller and smaller as time goes on. All right? It's 500, then 499, right? You get the idea. That's easy to accept that it is falling, and the value of s is getting smaller as t, time, is getting bigger. That's the significance of the negative. But also there's units. It's at this point we're doing science, and I know in science class, like it's very important to keep track of all your units. And this is meters per second. How do I know it's meters per second? Well, the units of this derivative would be the units of s over the units of t. And what was s? Position, and that was given to be measured in meters. And t was time, given to be measured in seconds. So this is like the derivative turns out to be the speed. It's falling at 93.1 meters per second. Okay? All right. So the math is not too difficult, I would say, but what I want you to think about are a few philosophical questions, finer points of the derivative. So think about this. If I tell you that the derivative of position with respect to time at the instant when t is 9.5 seconds is negative 93.1 meters per second, do you see a little bit of a contradiction in that statement? Okay? Well, think about it like this. So can you imagine something's moving 93.1 meters per second? Or can you imagine something's moving at all, like meters per second? Okay. How can it be at the instant when t is 9.5 seconds that it's moving? Because at any instant, nothing is moving. So I might think about it. At 3 p.m. today, at exactly 3 p.m. today, everything was standing still. Okay? So at exactly that instant, nothing was moving. So how can that number translate into the speed of the object? It's a contradiction between an instant and motion. For motion to happen, time has to be passing. All right? So that's my first finer point, that this does seem like a little bit of a contradiction. But that t is 9.5. That's the instant in what we would call the instantaneous rate of change for the derivative. The next thing, now we'll resolve this here in a minute, all right? But for now, I want you to think, yeah, I guess that is a little bit of a contradiction. How could it be moving at that moment? Doesn't seem like it could happen. Or if you imagine like photos, like if you take a photo of a moving object, sometimes there's a blur, but sometimes it looks like it's moving. It's perfectly still. It's kind of like that. It's a little bit like that. Not exactly, but it's a little bit like that. All right, so next thing is this right here. Does this mean that at, say, t is 9.5 seconds, if 1 second passes, does that mean the rock will fall 93.1 meters? Because I think 93.1 meters per second, it kind of sounds like if 1 second of time passes, then the rock falls 93.1 meters. Is that what it means? You know, if this is a little bit contradictory, maybe this is what it really means. Well, let's try it. So I have a little table here, and I said, well, I'll let t be 9.5 seconds, and I'll let 1 second pass, and that will make it 10.5 seconds. And I'll calculate the position, okay? And it turns out like if 1 second passes, now it's below ground. So that's one reason to think that, well, that can't be what it means. But if we just took these numbers to heart anyway, and we calculated the change in position over a change in time, it would be that it moved 98 meters in 1 second. So that can't be it either. So even if it could fall through the ground and keep moving, it still wouldn't be the case that in 1 second it falls 93.1 meters. So it looks like that both ways that you could try to understand what that number meant don't seem to hold up to reality, okay? So here's how we have to interpret it. Here's the right way to think about it. It turns out that this derivative is just a limit, okay? It's change in position over change in time as the change in time goes to zero. Okay, that's what it really is. The instantaneous speed when t is 9.5 seconds is just what you would get if delta t went to zero. All right? If you measured change in position over change in time, but you let the change in time shrink unimaginably small, that's what the derivative is. Okay? So that's why, like, if you found, for any derivative, if you found delta S over delta T, and you let delta T be really small, you would about get what the derivative tells you. All right? For that reason. So, and you can try that with any of them. So for me to say, well, the instantaneous speed, the derivative is 93.1 meters per second, then all that means is that, well, at that moment when t is 9.5, if just a little bit of time, very small amount of time, we're beginning to pass from that moment, this is about how it would be moving. That's the interpretation you can give to that number. Now, how does that relate back to some of the examples we've seen in the videos and problems we've seen on the quizzes? Is that, well, the derivative, okay, it's dy over dx, is the limit as delta x goes to 0 of delta y over delta x. But, because of that, the derivative and the delta y over delta x are approximately equal, so long as you let delta x be small. Okay? So yeah, I can sort of feel out that this is not right. Yeah, at any instant, nothing's moving. But if from that instant, a little bit of time passed, this is about how you see it behave.